Click the bell icon to get latest videos from Ekeeda.
Hello friends, today we will talk about the concurrency control in distributed databases in terms of timestamping and deadlock handling. We will know that how we can differentiate between a centralized and distributed timestamps, and also how we can conclude with an local and global wait for graph with the false cycles in them. The concurrency control involves the locking protocol as well as the weak level of consistency in this concurrent execution, which we have described in our previous videos. Today we are most concerned with this timestamping as a part of the distributed database. As we know, what is a timestamp? It is a logical clock or a logical time unit that is associated with each of the transaction. Now the transaction denotes with this timestamp that it is the start of the transaction, or we can say that whenever a read and write operation happens with the transaction. We can denote the TSTI as an timestamp that is associated with a part of the transaction. Now it can be marked with an SI, that means a system clock on which the transaction has started. Now with this timestamp we have two more that is related to it. For a data item Q, there are one write timestamp and another is read timestamp. So the write timestamp is known as W timestamp on data item Q. So it is the largest write data time that can happen on a data item Q. And another is R timestamp Q. So this read timestamp goes for the largest time for read that data item inside that transaction. These three are the basic units of transaction system on this timestamping. Now the timestamp can be given a logical counter onto an centralized and distributed system. Now the timestamping can move from centralized and distribute. In centralized, it has a local timestamp just like this TS that we have given to it. But in the distributed system, along with the local identifier or the timestamp, there is one more identifier that is maintained by the site. Now we are allowing that one primary site which contains the primary copy on which we can modify or update any replica on the data to it. Now we are concerning about more the data that we can have write on this data type on the W timestamp queue, because the write timestamp is the more concern on a distributed system, because the reading is not a problem, as we have seen in this locking protocol too, that the read operation can be performed by different sites at the same time. But the timestamp, if it is the condition to check that whether an write operation can be performed or not other than the locking, then we must ensure that this W timestamp queue is verified not only by the local site but also by the global identifier. Now let us define the global identifier timing on this timestamp of a distributed system. Now first we have a local unit timestamp. Now this local unit timestamp is often denoted by TSTI, that we can say then local unique timestamp. Now let us look at the keywords local and unique. That means it belongs to a particular site, and unique means if the TS is on TI, then there is no TS on TJ that can be equals to the TSTI. So every timestamp that belongs to a particular site must be unique to each other. There is one other site identifier which is known as the primary site identifier. So this basic function of this site identifier is to check that is any greater than timestamp that is belonging to the site identifier. So this is more known as a site identifier. So the site identifier is mainly concerned with the site that is being the primary site which is holding the primary copy. So the site identifier is holding this primary copy. Now the primary copy of this identifier will be made all the right transactions that we can have on this distributed system. Now then, what is the idea behind this local timestamp? Now the local timestamp along with the site identifier timestamp can be generated with the global unique identifier. So now my global unique identifier is consisting the TSTI as well as it having the timestamp of this primary copy. Now what we need to do that the global unique identifier is also a unique value. That means for each of the transaction, it will have an unique value for the global identifier. And we can say that this local unique TS must be less than the global unique identifier. So any of this local TS must have the value that is less than this global TS. So in this way, we can have that the local timestamp can occur before the global identifier has been identified that particular timestamp. Now in this concept, we are introducing the distributed system. That means there is one site which is responsible for generating an identifier to be combined with the local time system so that we can have a global identifier which will identify that the timestamp of this transaction can be compared with the other transaction from other site. Now say suppose if there is a global transfers on this TAG and now there is another timestamp for transaction TJG. Now this belongs to site A and this belongs to site B. Now if they are equal, then we can say that this is not a valid timestamp because we have already seen that TSTI must be less than TSG on TI. So now also TSTJ must be less than TSG TJ. So if these two properties satisfy, then we cannot have this TSTI is equals to TSTJ. That means any global identifier first need to identify the data on the transaction that it can happen or not, and only after that the transaction can be happen. So in this way we can restrict that no to write operation that belongs to an W timestamp can offer this operation to be identified by a global one. Now say if this TSTI is less than this W timestamp G on Q. That means the TSTI hash is issued and write Q, and now it is less than the W timestamp GQ. That means globally that value is not till now written and any local copy can be given the permission to write the data. Now what happens if this TSTI is less than this R timestamp GQ? Now if it is issuing this write Q and it is less than this R timestamp GQ, that means globally that value will not be read because that value was needed previously and now it will not be read after this one. So this write is rejected on this one. Now in this way we can say with the help of a global identifier we can either grant or reject a write operation onto the basis of this local timestamp and the site identifier. Now the local site identifier, how you can identify by a local site. So for each local site SI, there is a local logical clock which is known as LCI. Now whenever there is a transaction that arrives with XY, that means X being performed Y operation, and we can have this X satisfy this global identifier, then we can say that if TI is less than this LCI, then only the X can be advanced with X plus 1. That means the next transaction can be advanced in that way. Otherwise, all the condition will be falsified because the local clock or the logical clock that is associated with each local counter on the site will be false for any TI that is greater than LCI. That means now my TI is happening after the logical clock has moved, and the logical clock will only move when a transaction is advancing or processing. So this is logically wrong for TI greater than LCI, and we cannot advance our variable on any operation to that. So this is all for the time stamping on a distributed database to control the concurrent executions. Now, how can we handle the deadlocks in a particular distributed database? So we will talk about the deadlock handling in concurrent execution of a distributed database now. Now, the deadlock prevention and deadlock detection, both the algorithms that we have described previously, can be used in distributed databases too, with some modification, because now my tree protocol will consist of the system data rather than the database on the data were stored, and also the timestamp that we are fixed now will be considered with a global timestamp, and now we can be considered that particular transaction will happen after that the timestamping on the global unique identifier has been identified. Now let us draw some wait for graphs that are local to the systems. Now the deadlock prevention technique involves that we are having unnecessary unwaiting and this waiting for a graph. Now whenever we are having a wait for a request to be performed, maybe we are reaching in a situation of starvation and the rollbacks or the waits. Now this is not desirable. We can either let the condition to be in a deadlock and then detect the deadlock to avoid it. So for the deadlock detection algorithm, the most popular one is to draw the wait for graph for every transaction that belong to each of this site. Now we can find a global wait for graph for the sites if they contribute to a distributed operating system. Now in this local wait for graph, when to insert an edge, we will insert an edge Ti to Tj in the local wait for graph when there is one Ti that reads a resource from S1 and now it reads another resource from S2. That means if Ti wants to release Tj that belongs to another resource site S2 to release its lock, then we will insert an lock graph or the edge Ti to Tj in our local wait for graph. Now suppose say that our site 1 is having transactions T1, T2, T3 and T5. And our site 2 is having T2, T3 and T4. Now they are waiting in such a situation. Now T2 is waiting for a resource to be emptied by T1. That means the lock need to be released from T1 whether this resources belongs to this S1 site. So we can put from this T2 to T1 and directed edge. Now T2 also requires T3 to release an item which also belongs to this S1. So we need to put another edge from this T2 to T3. Now T5 request and recurse which is implemented by the transaction T1. So now T5 needs for this T1. So we can see that T1 is holding resource which is needed by T5 and T2 both, and T3 is holding a resource that needs by T2. Now in this S2 we are having that T2 is requesting for a resource that is held by T4. So now we will put an edge from T4 to T2. Now you can see that from T2 we are having T3 and T1, so it needs from T3 and T1, and now T4 needs from T2. So we can say that T4 is also waiting for T1 in a cyclic way, where these two graphs belongs to S1 and S2 to different sites. But as they belong to the distributed system, now we can see that one transaction from one site is being dependent on another transaction. Say for another example that this T5 is waiting for one transaction T4 to release its data, And also we can see that T5 is waiting T1 to release its data. So now T5 needs two resources. One is from S1, another is from S2 that it needs. But if it such condition rises that when T5 is waiting for T4 from S2 also and for S1 also, then there is a problem in the wait for graph and we have not run the wait for local graphs properly. So these are the local wait for graphs that we have made our deadlock detection. Till now we have not detected any deadlock in this local wait for, because we know that whenever there is no cycle present in the wait for graph, there is no possible deadlock that can be detected from the transaction involved inside a site. Now, if the same problem that is occurred in a centralized deadlock detection algorithm, that means now we are considering all the sites to be compared with a global unique identifier, or globally how it is connected to each other. So now we can see that there is a cycle present. Whether it is not present in the local identifier, it can be present in the global graph. Now, if this one is used by the global unique identifier, now this is my global wait for graph. So in this global wait for, if we made this local wait for, as there is one coordinator which we can say that is in a single system coordinator. That means now it is considered as one single site S and being the coordinator of this deadlock detection. So what does a coordinator do? The coordinator can perform that the combination of this local wait for graphs. So now if we can put, and it can be seen by the coordinator, like therefore T1 we are having it from T2 and also from T5. Now for T2 we are having that it wants for T4 and also wants for T3. Now we can see that T3 is involved in our local wait for graph at the S2 where it wants from T5 too. Now the T5 is being made for this T1, so there is an inherent part of this T3 to T4 in this cycle. So what are the coordinator that it is introducing? That there is a cycle in the global wait for graph. That means if the local systems are handling these deadlocks, there is no deadlock in these sites. But if the sites try to communicate with each other or concurrently execute with each other, then there will be a deadlock, because now there is one graph from T5 to T4 which we cannot plot in this one. Now we are plotting it via this one, that T4 wants from T2, T1, which T5 wants for. So now T3 to T4 there is one requirement, which is the global requirement, not the local one. Now the concept of false cycles arises. So when there is a false cycle, we can say that the coordinator can generate a false cycle Ti to Tj when for the graph in the local one we are having Tj to Si if the Si is the site on which the resource needs and Si being the site on which the resource is attempted to have the request. Now we need the coordinator to generate the graphs as much as smooth possible that it becomes correct. What do you mean by that producing and correct? That whenever there is a deadlock detection in this type of Google Earth for graph, then we can have that the cycles are correctly producing the deadlocks. It is not like that we are producing the false cycles. So what we can do, whenever there is an updation into the local wait for graph, we must produce that one into the global wait for graph too. Now in this graph, we cannot see there the T5 to T4 update that we can make here. Rather, we are making a T3 to T4 update because in turn it needs the T4, T2 to T1, which also needs by T5 to T1. So now this T4 and T5 graph, which is represented by this via T4, T2, T1. So now T5 to T4 is being represented to T5 to T1, T2 to T4. So now via this path there is a cycle in this coordinator graph. So there is an update or change in the local weight for graph, we must change it into the global weight for graph. If periodically there is a change in the local weight for graph, say for an instance that we have constructed the local weight for graphs and after that we have constructed one global weight for graph, but we have not updated that if one transaction is being aborted or committed or release the logs. So this must be represented in the global weight for graph. And finally, if the cycle detection for the global weight for graph is true, that means if there any cycle detects, then we need to look at the local weight for graph that what changes we can make or what transaction rollback we can perform so that we can achieve in a deadlock free situation. Now what happens for the false cycles? Say for an instance at site S1 there is one updation as per the global coordinator that T2 has released the edge where it can happen the T1. Now T1 is having this requested data locked on this transaction. Now again T2 has requested for it. So we know that the timestamp cannot allow us to have more than one locks at the same time. So now in false cycle that is T1 to T2 exists in this S1 graph. Now in this one we are having T2, T4, T5 and we are having this T2 to T3. So by this T1 to T3 there will be one more one that T3 to T1 that exists in this S2 graph. So by false cycles we are having this T1, T2 and T3 to T1 because they do not exist in physical condition but logically they are implemented. So if we have detected this much cycles in our wait for graph, then even if there is no deadlock, we can detect it and cannot get recovered from it. Let us draw the false cycles that can arrive for the wait for graphs. Now say for the S1 we are having one false cycle for T1 to T2. Now for S2 we are having from T3 to T1 as an implementation that T4 was being attached with T2 in this S2 where we are having T2 has been attached to T3. Now how the coordinator will imply these false cycles? The coordinator will see that as T1, T2 and T3. So there is one from T1 to T2 and one from T3 to T1. So it just absorbed and false cycle by this coordinator which involves T1 to T2 to T3, which is not a desirable one. Now we can omit this type of false cycles by giving that the most one which can have at the time when there is a new edge in the local wait for update in the global wait for immediately. Now say suppose that the deadlock has indeed happened in this detection algorithm. Say for this T1 T2 which is being a false one and this T2 T3 or T1 T3 which is being a true one to create the deadlock cycle for our example. Now for this local wait for graph we need to roll back T1 and T2 both, and this coordinator graph needs this T3 to roll back also because we want all the transactions to be rolled back if they belong to the cycle. But in fact or in situations on a real-time basis only rollback of T2 is sufficient to break the deadlocks. So it is not always able to get the wait for graph as an example to detect for the deadlock which can be a false one, and even if it is a true one then by detecting the deadlock for this coordinator graph and delete the data based on it, it may give us an extraneous work that is rollbacking T1 and T3 also where only T2's rollback was efficient to give this transaction at deadlock-free situation. So in this way, we can handle by a distributed system while we can maintain the concurrent execution in a consistent way inside a system. So that is all for the timestamping and deadlock handling. Thank you for watching this video. Stay tuned with Ekeeda and subscribe to Ekeeda.